Welcome to the DornerWorks seL4 Doom Pendulum demo. This is the longer video that goes a little more in depth and more technical with some of the aspects of the project. Team introduction. So we are Team 4, the DornerWorks Senior Project. From left to right, we have our faculty advisor, Dr. Krug, Joel Myers, Alex Kaiser, Eric Speidel, Mitchell Sherwood, Alex Konworski, and Owen Gibson. So what is our project? Our project is meant to show off a hypervisor, which a hypervisor is just a piece of software that allows multiple operating systems to run on one piece of hardware. So in this case, that hardware is the Ultra 96, and we have two operating systems running on top of that. One running the game Doom, and the other running an inverted pendulum. And then there's also a giant red button, which when you press it, it kills the Doom game and leaves the pendulum running. This is to show the isolation between the two operating systems. Even though they are on the same piece of hardware, they are completely separated, which is one great advantage of the hypervisor. The specific hypervisor that we're using in this case is seL4, so we'll talk a little bit about that now. It was developed in Sydney, Australia. It's formally verified, which just means that there's a bunch of proofs out there that basically prove you can't do anything super malicious with the code, which the Department of Defense and other defense sector companies really like. It's also an operating system, but in this case, we're using it for its hypervisor capabilities. And like I said, it's valued by the defense industry. It also has very high performance for being a formally verified kernel. So there's other verified things out there, but they're not as fast. So seL4 is both fast and secure, which gives it a great edge over a lot of other pieces of hypervisors out there, excuse me. So the demo was started by DornerWorks, and the whole idea is that we want to show off why you'd want virtualization and how it gives that isolation. And so as you can see over here, we have the Doom game running, and then here's the Pendulum itself actually running. And if you note, you can see, so Doom VM and Pendulum VM. VM stands for virtual machine, which is just an operating system that's running on the hypervisor. And then the hardware down here, we have, of course, the monitor and the controller for the Doom VM, and then the button as well for that one. And then the big thing for the pendulum is this pendulum here, which is what controls it with motors and encoders. And then the Arduino, when we got the demo, acted as a liaison between the Ultra 96 and the pendulum. So it was basically sending and receiving data on what to do with the pendulum. And we'll touch on that a little bit more and why that's kind of confusing. So here are the key specifications that we needed to make sure we achieved in order for this project to be considered done. The first was removing that Arduino. So like I just touched on, it's a little confusing. When you see the demo and you see an Arduino controlling the pendulum, you would think that, oh, so the Arduino is controlling the pendulum and then the Ultra 96 is running Doom. That's not the case, but it is easy to get that confusing, or easy to get that confused. And so one of the big things was actually removing that Arduino. And we want the motors and encoders directly to be controlled directly by the Ultra 96. So we're going to do that through AXI, which is an interface used by Xilinx chips. So that was one of the big things. And the way we achieved this was mostly through code changes, as well as a couple of things on the shield that sits on the Ultra 96 itself, which we'll get into a little bit right now. So we have the mezzanine board or the shield. This is what sits on the Ultra 96 so that we can make all those connections to the motors, encoders, that push button, stuff like that. And you can see there's also some VM LEDs which show status. We'll touch on those a little bit later. The big thing for this, we needed to fix a couple of the level shifters. They're bidirectional and a few of them broke. So the shield didn't always work as it should. It got a little messy. We fixed that, and we also made the board 4 layers, I believe, instead of 2. So it has its own ground plane and stuff, which is a lot nicer. And then a couple other just cleaning things up and adding a little bit more detail into the board itself. Another key specification that we needed to clean up was the algorithm itself. So the algorithm itself was initially running on a Linux virtual machine, which was a lot of overhead. So it was just one single process inside a full Linux VM. Very overkill. We definitely did not need all of that. It was also written in Python, which is a lot slower than a compiled language like C. And so it had a slower runtime, of course. Our job was then to convert that into C so it was compiled and it ran faster. And then along with that, we needed to change the Linux VM into a FreeRTOS VM, which is just a real-time operating system, and that is just code that's built to run and respond to events really quickly. So it's a lot faster than Linux, both, and it's more lightweight as well. And so that was one of the main things. And of course, we did that by mirroring some of the C code off the Python code and then making changes where needed, tweaking values and stuff like that. Our final key specification was the VM status. So those LEDs that I touched on a little earlier, those are supposed to show, if the VM shut down, if it's rebooting, or if it's, good to go. So green would be it's running, yellow would be, oh, the VM's booting up or it's rebooting, and then red would be that the VM is off. And remember, the VM is just one of those operating systems that's running on the hypervisor. So either the Doom VM or the Pendulum VM. All the LEDs share a single GPIO pin. That was pretty cool that we were able to do that. That was a little tricky, but we did figure that out. And a lot of that was just getting the hypervisor to actually write to the certain address that we wanted for these LEDs. But once we got that figured out, this was not too bad. And then, of course, here's a diagram showing the virtual machine states. So, and what the lights would be on those certain states. So, of course, we start with off. Everything's off. We switch to on. They both go to booting. Once they finish booting, the pendulum waits for the user here. And then once that is set up, that all goes to green. Doom turns to green when the game's playing. And then if you press that kill button, Doom gets switched to off, but this stays green the whole time after it basically gets set up by the user here. So it's important that this one stays up even if Doom turns off, because again, that is the whole point of the demo. We want to show isolation. Here are a couple of our builds throughout the project and kind of some stages of where we were at certain points. So again, here's the existing demo. It's got that Arduino. Over here, there's also a battery, and there's the button. So this caused a lot of confusion, and we really wanted to get rid of this. And of course, you can see Doom running and the pendulum bouncing back and forth. So our first thing that we did was we tested what was going to be our PCB design on a breadboard. And this is that picture right here. As you can see, it's a little messy, but we did get everything to run, and it looked pretty good. This was what the initial algorithm looked like without the Arduino, excuse me. Very back and forth and jittery, extremely messy. Definitely not like their version. So we had quite a bit of work to do. Here's our first revision of the PCB. Important to note that this wasn't necessarily from the hardware design. It was more from a software thing, which we figured out later, but it was just something to note. And so here's our Rev 1 of the PCB. This had a little bit of an issue. We had a voltage drop across a transistor that was ruining the way the motors were driven. So that was a problem. So this is why it was Rev 1. We did find a workaround just to get this to work and test with it, and everything else on it worked fine. But we were ultimately going to end up with a Rev 2 later for that reason. And then here you can see a little better algorithm. It's kind of grainy, but this is again with tweaking software, especially the RTOS, and then some of the values that go into the control theory of the inverted pendulum got tweaked as well. And it definitely is improving, but it's still not where they had theirs. Here's our Rev 2. So we removed those transistors. It got everything situated with that. It worked a lot better. No issues with this one, and it looks a lot cleaner as well. We also added some, Doom Pendulum demo right there. Looks really nice. And then I think we moved the DornerWorks logo over a little bit. Here's an in-progress build of that. You can see the lights are actually on this time, so that's pretty cool. And then this is just a prototype connector. We'll have a nicer connector that shows up in a little bit. You can see the push buttons plugged in, the power. This is the Xbox controller. And then this is just a UART port so we can see what's going on, but that won't be in the final build. And here is our adjusted algorithm. So it looks pretty good. Still does a little bit of swaying, and we'll end up fixing that just by tweaking some things in the software itself, but nothing too crazy. This was, I guess, our breakthrough kind of where we finally got everything working without the Arduino the way we wanted. And then it was just tweaking and cleaning up things. Here's our final build. So it looks a lot nicer. You just have the button, the controller, just this one wire that plugs into the shield, goes and controls all of this, and then you'll have Doom up here, which you can't see right now. And then we also made new encoder and motor mounts. These are a lot nicer, and they match actually the PCB color, which is pretty cool. So, and now we'll show the final demo. So as you can see, I'm trying to full screen it, but um, this is moving a lot better. This looks very similar to what DornerWorks started with. You can even mess with it and move it around and stuff, and it's really not gonna fall over unless you really push on it. You can see Doom is running there. You got the LEDs running. They're both green because both VMs are up. I'm gonna press this button here. That's gonna kill this, as you can see, but this is gonna continue to run. So perfect, just what we wanted. It's hard to see, and I'll show you a little bit later, but that LED does turn yellow. Um, so yeah, Doom shuts down, restarts, and then this just continues going like nothing ever happened. Again, the whole point of the demo is to show that isolation, and so we're really happy with how that turned out, especially because there is no Arduino, so it's a lot more clear on, okay, this is the same piece of hardware, but they are completely separate from each other. So we'll wait for that to boot back up. And there you go. So Doom is running again, and then of course you can see these LEDs, and there's all the connections. So that went to yellow. Somebody pressed the button again, and then it would restart again and start over. So that is the Team 4 DornerWorks Senior project. I hope you enjoyed.